Okay.
Okay, go.
Hi, everybody. So I'm Emma, and this is the Capstone team. We can all introduce ourselves as we kind of speak. We had a presentation earlier this week for our actual Capstone class, but we're going to kind of just shorten it and make it more of almost a kind of discussion for today for you guys, because there's a lot of background that I don't think everyone here necessarily needs. But basically for our class, and the scope of this project is to create a research reactor for Dr. Skip. They have an existing reactor, as I think everyone knows, that they've been using for the last few years. And because of some new requirements that have come up, and the kind of difficulty of use of the current reactor in certain scenarios, Skip decided he wanted a new design. And so it's been our job to create that. Let's see, I think that's a good intro. Yeah, I don't know. There you go. Hand it off to Kieran.
Hey. My name is Kieran. Starting on our design process, we developed a list of customer requirements, and from customer requirements, you can generate correlated engineering specifications. So what's really important about that is taking what your customer wants and turning it into something measurable, something we can design with. So like you want the reactor to be tall. So we say how tall, and you say 30 inches. That's not what this is, but just as an example. So we spent a lot of time talking to Skip and talking amongst ourselves to come up with those requirements. And some of the key ones that we found were that we wanted to minimize the reactor maintenance. And so part of what that meant as a correlated engineering spec was we want to Skip on 0 moving parts, and the reactor will have 0 moving parts. And we also wanted to create a reactor that would last. So we want to use parts in our design that will have a lifetime of about 2,000 cycles. Was it based on 5 years of use, Skip? We came up with that number.
Yeah, about 5 years.
Yeah, about 5 years. Were some other big customer requirements?
Safety.
Safety.
Safety is an issue.
Safety is a big issue. So our kiln design meets a couple of customer requirements. It should provide uniform heating for the reaction, and it should provide really good insulation is our hope, as well as being a lot cheaper than buying. We had considered buying and retrofitting a kiln at one point. But yeah, so the customer requirements are important to help narrow our project's scope. One of the things that Skip wants in the future at some point is a way to collect and possibly recycle the non-condensable gases. But with our customer requirements, we decided that that was outside our project scope because we just don't have much time. Yeah, so Adam can talk about our concept generation.
So I'm Adam. So before we actually began our concept generation, we first needed to get a better understanding of how pyrolysis works overall. So we met with the Plastics to Fuel lab team, and they kind of gave us a little demo on the preparation and how the reactor operates. And this kind of allowed us to see what issues operators were having when setting it up, what issues we saw when we were watching it run. And then this allowed us to kind of generate ideas on our own. And we each took about a week individually to do extended research, develop our own concepts, about like 2 to 3 concepts per each subsystem that we have for the reactor. So we generated about 30 concepts overall, and then we kind of met back up and then discussed everything together and kind of began down selecting. We use a thing called the Pew chart, and basically it allows you to compare each concept to the reactor design. So that's essentially what we did. We kind of down selected concepts and eliminated what we thought maybe wasn't a good idea. And then once we kind of had those finalized concepts, we brought them to Skip, explained it to him, he gave us his opinion, and then that kind of helped us finalize it down to what you see here today. So.
And I'll just kind of break in and say that we broke the reactor, the existing reactor, into, was it 6 subsystems? 5 subsystems. We had the main compartment, which is where the plastic is loaded and heated, and then we had what we called the resonance chamber. Skip calls it the packed bed, where currently the Raschig rings go. So we separated those into 2 different subsystems: the condenser, the heating elements, and the control system, and the insulation. So yeah, 6. And then with those subsystems, as Adam said, we generated concepts for a bunch of them, and yeah, came up with this design, which Avery is going to talk more about now.
So I'm Avery, and this is our prototype of just the kiln and the reactor. So this combines the insulation, the heating elements, the main chamber reactor, and the packed bed. So the insulation is on the walls and the base of the kiln, and that will be a soft brick, fire brick, soft insulating fire brick. The frame will be made out of just angle irons and will have legs on it, so it can be propped up off the ground. This is our roof for the insulation. It's going to be some kind of sheet metal with an insulation on the bottom, and it just like fits around. It'll fit around the main chamber like that, and be removable. And this is our main chamber and packed bed. We decided to combine them, and we're going to have a little welded square or some sort of stop to put in here so that the ratchet rings or some other sort of packed bed can go in here. We figured this would minimize issues with bolts and be an easier setup. And then the heating coil will go on the inside of the kiln, and we'll just route it in here. We don't have it in the prototype, but it'll just be routed around all four walls to heat the reactor. And then Adam will talk, or sorry, Andrew will talk about improvements.
Yeah, so some of the things we learned kind of from our prototyping process was really like dimensions and then features. And as far as dimensions go, we're going to make the kiln a little bit smaller. We realized it was a little too big for the hood that we're designing it for, and then also we have extra room as far as for how big of our main chamber is going to be. And then our angle iron frame, we're adjusting the dimensions there, so the angle iron will still provide the leg feature like we have here, but it'll extend up to the top so that the lid will fit inside of the angle iron, which is extending up a little bit, so that'll kind of hold that in place. And then as far as features go, we had debated prior to the prototyping process whether the bottom of the main chamber should be removable. And now, when we built it to scale and are holding it in our hand, we decided that it should be removable because it'd be pretty hard to clean the bottom just based on the height of it. And another thing I wanted to note was that we increased the diameter of the main chamber slightly. It goes from about 4 to 4.5 inches, which is helpful because we can achieve the same volume and reduced height. So this is the main chamber where you'll load and the ratchet or residence chamber all in one. So it's quite a bit shorter than the old design. Oh yeah. So the residence chamber has always been a little bit of a black box to us. We're not entirely sure what it does other than reduce the volume or reduce the area which the gas can travel through, which slows its release time. Yeah. So one thought we had and something we want to prototype and potentially test in the old chamber is having a disc, say, that was the same diameter as the inside of the pipe, and then you could put holes in this disc, and these holes would allow the gas to travel through it, but it would slow how quickly it would travel through. And you could potentially have many holes to have that surface area feature that the Rashig rings provide. And the idea is that you could potentially have multiple discs stacked on top of each other. And we think that would be a little more sustainable and measurable way to kind of model or apply that feature to the reactor without kind of the black box of some amount of Rashig rings poured into the disc or into the chamber.
Yeah, so those are kind of the basics. I know we didn't go into a huge amount of detail, but that's our prototype so far. And we'd love to hear if anybody has any questions or concerns. we've thought about this a lot, but I know there are questions. Go ahead, Skip.
Yeah, so I just wanted to know if you could comment on it picks up. Okay. On what we talked about for the wall thickness and the materials of construction and stuff like that. You didn't mention that.
Yeah, so the existing reactor is made out of, as far as we can tell, a low carbon steel. But we know it's not made of stainless steel. We know it's some form of steel. And as it is now, when it runs up to the temperatures that they're running now, which is 500,
450.
450, it turns bright red, which makes sense when we look into the material properties and find that low carbon steels are not meant to run at such high temperatures, which is obviously a huge safety concern. If we're sustaining those temperatures for a long period of time, running lots of tests at those temperatures, then we can see serious deformation in the materials. And it's scary seeing a bright red reactor as you're running it, I'm sure. So the biggest material change that we decided to go with was switching it to 304 stainless steel. And we're also most likely going to change the wall thickness from schedule 40 to schedule 10, which brings it down, I think, like a 0.12. I think it's 0.12 inches now. I don't remember exactly what schedule 40 is.
No, I think it's 0.24, but it's
0.2.
thinner. I don't know.
Okay, yeah, it's thinner, and that should decrease weight. It should increase the heat transfer through the reactor, since the heat is coming purely from the outside. Because of course, steel and stainless steel are not super conductive.
So stainless steel has about half the thermal conductivity that low carbon steel has, and so that's why we want to reduce the wall thickness so that we can achieve the same or a similar amount of heat transfer, but using the material that's actually rated to the temperatures we want right now.
Yeah, so that's an exciting change. And what else?
Can you talk a little bit about the maximum temperature you can achieve in here and what these bricks are made of, and what's the maximum temperature you can get with the 304 stainless?
The 304 stainless can hit about 825 or 850, slightly over 800 degrees Celsius. The fire bricks can get up to over 1,000 degrees Celsius. At least a lot of these kilns that people build at home using these, they're 2.5-inch thick walls. So this foam board is not that thick, but if we use that same wall thickness, those kilns run at over 1,000 degrees Celsius.
So it's well over designed for what temperatures we expect to be running it at.
Yeah.
And you could potentially do tests at higher temperatures if you wanted to.
Yeah, with the heating coil, we'll be able to, you can increase temperature if you need to. You can also use for the 120 volt plug instead of a 230 volt plug.
That's the hope. Yeah.
Yeah.
One more question. What did you decide for the wire for the heating coil? Have you talked about that yet?
Yeah, so we're going to use resistive wire,
So candle wire.
candle wire. Here, you go ahead, you know more about this.
Yeah, so you can buy spools of fairly cheap wire called candle wire, and with the wire, all you have to do is figure out what the maximum amount of current that you can pull from your outlet is. So it's probably going to be about 13 amps. And then based on that 13 amps, that will tell you how much resistance you need your wire to have. So you can calculate how long you need the wire to be. And then based on the space we have available in the kiln, you coil the wire into a spring shape, and we can change the diameter of that coil based on our available space. So the candle wire is just like it, and you just wire that through a solid state relay to a PID controller, and then like
Sounds pretty simple when you talk about it.
Any questions from the Zoom audience? Scott or Kevin or Bianca?
Yeah, I think I just had two. First with the removable bottom, I see that as a risk. It's something you won't be able to see what's happening when the reactor is running. And so if you did develop a leak, you could have more of an upset condition. Was that added? Was the idea that you would need to take that out because you'd have unreacted material? And if so, are you considering the fact that you're making a better reactor and you would likely, hopefully have all just char in there that would be pretty easy to remove from the top of the reactor?
I think that design change came from the customer requirement of having it be easy to clean. And the current reactor has a removable bottom, doesn't it?
Which you do make a good point of, because we're closing it in a kiln, we won't be able to see it. However, the current reactor, the way you run it right now, excuse me, and this isn't a good reason to do it, but the way you run it right now, you also can't see the bottom because it's sitting in that jacket and covered. So that's not a big change, and I know Skip did want to have the bottom be removable. But that's a good question that we should probably look into if the reaction runs more to completion, if we need to be able to take all of it.
We're also planning to have some sort of metal square welded into the, close to the top of the reactor. So that'll also hinder being able to reach down the bottom if you need to clean it.
Yeah, so the idea of having this all-in-one reactor while still including that packed bed means that we have to have, like Avery was just saying, it's like sort of a ledge or a bracket inside of the reactor, which could make loading and cleaning a little bit more difficult. So we were trying to consider different ways that could be helpful for cleaning. The discs are one way, making a disc assembly that can be removed all as one piece as opposed to having ratchet rings come out. But yeah, that's definitely a consideration, having the possible leaks and that kind of thing. Yeah.
And by the way, Scott, Emma's laptop's over here, so
Sorry.
we can look you in the eyes or we can look you at your picture.
Sounds good. I guess, adding on to what you just said about having a bracket inside the reactor that could cause it to be difficult to clean, you could also suspend off the flange a basket that could hold your ratchet rings. And I think it's worth looking into the ratchet rings that you want to, I guess it's more than slowing down the vapor. We're really trying to get intimate contact between the vapor and the liquid that's condensing on the ring. So that's something if you look at alternatives like disc or some other type of transfer media, that would be something to think about. And I think Kevin has a lot of experience with that type of stuff.
Okay, all right. Thanks.
Yeah.
Thank you, guys.
Yeah, thank you so much, Scott.
So Scott, this is a takeoff on your idea of spending the $5,000 for a furnace, right?
Yeah, go with the furnace. I like that idea.
I was really surprised when Skip said that was an idea that you had considered because it felt so out there. But yeah, I think it was initially Andrew's idea and kind of on the same idea you were just talking about suspending some sort of basket. Initially, we wanted to have a removable inner chamber in the reactor so that it could be easy to run multiple batches or run a batch, pull it out, have another one ready to go and put it in. And the heat transfer and the material expansion of that idea kind of got a little complicated, along with all the different moving parts. And this kiln idea was originally an extension of that. I don't know if you want to talk about your kind of thought process behind the kiln.
Not a whole lot other than Emma kind of said it, but we were trying to look for ways where we could cycle our system quicker than heating it all the way up to completion and then letting it cool completely down and then using the same chamber again because it's got heating coils on it and whatnot. So we were trying to find a way to kind of detach those systems so you could cycle easier.
Of course, that kind of it didn't tie into the final product, but the kiln idea was such an interesting one. We started looking at buying kilns and retrofitting them. And then, I think Avery came across some homemade kilns and that sparked all these different ideas, which has been really cool.
I think it'll be way cheaper than 5,000.
Yeah, you told me it was going to be $180.
A couple of the people we found who built lab kilns or just bench scale kilns for home use have quoted that before the PID controller, they spend about $200 on materials. So the fire brick, the high temperature silicone putty to seal it together, the angle iron, the heating element.
We might be able to match that with the kiln itself. The reactor is kind of where things get expensive.
And the control system.
Yeah, the control system.
So one more interesting thing about the main chamber is by increasing the diameter and going from schedule 40 to schedule 10, it actually like cuts the price by like 60%, which isn't really what you'd expect because we're getting bigger. But with that reduced wall thickness and with that particular inner diameter size, it's a common pipe that I think is cheaper because it's more used more frequently.
I just wanted to add one thing, and I just was thinking about this. We could easily make 2 reactors, and you could actually just flip them in and out, just like you were saying.
Yeah.
And so that is another advantage in terms of turnaround time for here.
Yep.
Yeah.
And then another thing we like about the kiln idea is it's scalable. With heating coils or something like that, I don't know. I mean, I guess it might be possible, but you say you find 24-inch heating coils if you wanted a really big reactor. Whereas with something like this, you just build a bigger kiln and you get a bigger pipe, or you have multiple pipes inside of the same kiln, or something along those lines.
One other thing is, we talked about this for underserved communities, it's much easier for them to build a kiln or like a fire pit or whatever than it is to have heating coils, right? So it's better for the longer term goals of getting it into underserved communities also. Kevin, you have any questions, comments? Usually do.
Yeah. Yes. First of all, nice job, guys. Good presentation. My curiosity only centers around the heating elements and how you are going to hope to achieve a relative uniform heating profile around this, the reactor. One of the things I think you guys have done very well is to understand that you can, by making your own sort of heating system, you can certainly try 20 different configurations of, geometries and thicknesses and all that, and currents to get what you hope to get. In my world, you hope to get uniform heating around the plastic. So how do you expect to achieve that with, sort of out of the chute?
Yeah, we actually just spent like an hour talking about that. One of the big questions was which walls and how many walls do you put the heating elements on? Because the guides that we were finding online with people that built these, they're just doing it for ceramics or some small scale chemical reactions. So they provide a lot of heat, but they might not need to be as uniform. So the one really good example we found, he used the back wall where everything was wired together, and he ran 2 coils, one on each side, just in a U shape that went in and came out the back. So what we were just talking about is in like standard pottery kilns, usually they go around in a spiral with a single or a couple of different heating elements. So for our uses, if we still wanted a wire on the back wall, if you came in on one wall, circle the kiln at the top, and then move down at the diagonal on the back wall, you could get another full perimeter on the bottom and come out. So essentially you'd have 2 loops of coiled inside the kiln, and hopefully that would provide a uniform enough heat for the reaction.
And I think you're definitely right in that we're going to be doing quite a few trials on getting the exact size of coil and the exact, well, size we should be able to calculate at least, but getting the exact arrangement and the temperatures that we need from it. It'll be really interesting, but we have an entire other term that it's all about iteration and new prototypes. So that's the plan for next term, is to take what we have now and expand on it and actually figure out those details that we haven't been able to kind of look into in depth yet.
So one more thing I'd say about the uniform heating is that was another big benefit to moving to a design like this instead of like heating coils, is our heating elements aren't, I wouldn't say they're, from what I understand, they're not directly applying the heat to the chamber. They're heating the kiln. And then inside the kiln, we're hoping to expect a somewhat uniform temperature throughout the kiln, which should, we're expecting heat the pipe uniformly as well. And we can do cool things like we had talked about how we wanted the bottom to be heated. And we plan to suspend the main chamber about 1/2 inch off the bottom of the kiln ground, so that we're getting that same kiln temperature being applied to the bottom as well of the reactor.
Yeah, that was, I think, an issue that was happening with the current reactors, that there was possibly non-uniform heating on the bottom. And so that was another pretty big customer requirement from Skip, is wanting uniform heating. And this was definitely the strongest in our, when we evaluated all of our concepts.
I think you guys have given yourselves quite a bit of versatility, or to be able to play around with things like that. And I think suspending your reactor just slightly off the bottom is actually a very, very good idea. There's a few more I could throw your way, Skip, but I don't let your students figure that out.
Well, I was just gonna add, Kevin, in Kevin's design for his candle reactors, he has air circulating. I think, right, you have air circulating throughout your candle reactor there.
Yes.
And I was just wondering, could we set up a little fan system in there to circulate air also that way, so you don't have dead spots?
Could potentially do that from, you could maybe install one in the lid if we could find a fan that could handle the temperatures we expect the kiln to get to. Because the convection would definitely help the heat transfer. That's another thing we're just talking about. We think that the air will probably be pretty still inside the kiln. So we were thinking that most of the heat transfer is going to be through conduction, which would be small through the air, but radiation will be the big one. So that the convection is a great idea, Kevin.
Right. The one of the things that if you go over to the chemistry department, if they have gas chromatographs, those are reasonably high temperature machines. They're not as high as temperature as this, but they have, all GCs have a fan in them that keeps the uniform heat on the column that they're doing chromatography in. So you might just check through those guys, and because there's high temperature fans out there that will handle this heat. Obviously you don't want to move cold air in and heat it. You just want to circulate what you have.
Yeah.
Kevin, are you suggesting stealing a fan from the chemistry department?
Yeah, this meeting's being recorded, Scott. You did not say that.
I think to save Kevin, I think what he meant is that we would go over there and ask somebody if they had an old GC that they weren't using and that we could take parts from.
Yeah, well, that's the university way, isn't it? You guys are all bootstrapping in that regard.
Yeah.
Yep, that's
This
right.
is all made out of material from Skip's storage. So.
Anything else, Kevin or Scott?
Guys, it's a good idea. It's a good approach. I think I do think that the angle. So one of the things I know that we work with, and Scott, who I've worked with for several years at Agilix, we know thermal expansion, materials of construction. You just have to make very careful that when you're putting these things together, that certain things don't expand differently from other things that are going to create stress points, right? Make your angle iron running up just slightly above the top of the brick so that you have a natural channel for your covers is a good idea. Again, as long as everything's made out of the same material, so it expands and contracts, identically. That's just a big thing. But it's a great first swing of the bat, guys. Very impressed.
Thank you.
Thanks, that's really helpful.
I was just wondering, so are you planning to still control the temperature from the internal temperature of the reactor like we are now, or?
Yeah.
Want to repeat the question?
Yeah, so Kayla was asking about how we're planning on controlling the temperature, like which thermocouple we might base it off of. But we didn't even talk about the thermocouples. So the idea with, along with the disc assembly that we're hoping to put in the residence chamber, is that we could insert a thermocouple from the top all the way down through the center and have it measuring the plastic in the middle of the plastic.
Which is nice, because then we don't have to put a thermocouple on the bottom and bend it out. And also it would be out of where everything is heated, so you don't have to worry about burning up your thermocouple plug, which has happened apparently.
Yeah, we're trying to obviously limit the amount of wires that are in the kiln, and that way if we're just measuring the plastic but through the top, then we can have a full idea of the exact temperature of the plastic inside, but not have to worry about the wires being too all over the place. And then have, one other temperature reading in the residence chamber and one at the outlet of where the product comes up. But
We're also gonna put a thermocouple through the kiln wall, because you can actually buy kiln thermocouples that they come covered in the same fire brick material. And so that way you can put it through the kiln wall, but then not worry about losing heat to that hole. And that way we'd also be able to measure the temperature of the kiln chamber. Kind of comparing those measurements and see how our heat transfer calculations maybe hold up against real life.
yeah, but yeah, as far as controlling it, it'll be that central thermocouple. Ideally, that's the idea.
Hey, Andrew, can you put put it back in the kiln for a second? So one other feature that I don't think they mentioned is the bed itself, the residence time distribution bed is sticking out, so it can be cool. But if you need to heat it, you could also put some of that fire brick around it and make it hot also, so.
Or just a band heater.
Or a band heater or something, yeah, but.
It's taller.
Yeah.
Yeah,
You could just
but
stack them.
if it's something that you wanted to change from run to run, you could just put some fire brick around it like this and
Yeah.
control that,
Or
so.
even just jacket around it.
Yeah, I was gonna say, or even just like, we could make a different set of doors that allows more heat out just in the center or something.
Anyway, that's something that is not a hard design change.
Oh, and there's also going to be a nitrogen port.
Oh, yeah,
That will be, we raised it just enough so that the residence chamber will be somewhere around like here, and then the nitrogen port will be just below it, but above the kiln. And the idea was to flush out any oxygen and make it a fully inert atmosphere inside.
That's actually a really good idea. You can do what they call a huff and puff operation, where as you slowly heat it up, you insert and push nitrogen through 5 or 6 times. And that gradually, as your environment gets hotter, gradually sort of voids the space of oxygen. It's a good idea.
Okay.
anything else, folks? Scott, Kevin?
It's a nice job, guys.
Now you guys answered my question. Thank you.
Thank you very much.
Thank you guys so much for coming.
Yeah, thanks. everybody.
Yay.
No worries.
All right, good night, folks. I gotta go home and feed the dog, so I gotta run. But thanks very much, and we'll have this recorded. Emma can send it to us, and then we can show it to the other people in the group.
And I want to say, please feel free to reach out to us at any point if you have more questions or ideas, or yeah, if you're just interested and want to stay up to date, we're happy to keep anyone involved as we move through this.
Yeah.
Thank you so much.
Okay, and Kevin, while I have you on here, if you're still there.
Yep.
You remember you had mentioned something about a robotic cleaning of something or other at one point, and I need to talk to you about that because they want to know if you're interested in sponsoring that for next term, not for these guys, for another group. So I'll get back in touch with you with that. I just keep forgetting to do it, okay?
All right. We'll talk later on, Skip.
All right, have a good night. Thanks a lot.
Thanks, guys.
Scott.
Appreciate it.
Take care.
Everybody.
Bye-bye.
Oh, you gotta do it.